This morning, Stephen is going to talk about domain-specific languages for convex optimization. So this is he said it's going to be a slightly more technical talk. But I think even this is more technical. I think all of us should be able to understand, isn't it? If not, he will test us.
I hope.
He'll give us a quiz later. Let's give a big welcome to Professor Boyd.
Okay. Well, I should say a little bit about the talk today. So I guess early in the year, I gave a talk that was an overview. It wasn't very technical, but it was just about what can you do with convex optimization. But there was not much math in it. This talk is going to have the math in it. So just in case you're expecting the overview. By the way, the overview I'm actually going to give at CUHK in Châtillon on Friday. So if for any reason you want to see the overview, you could go there and see it. Right. Oh, also, this talk will not be like the talk I gave yesterday, which was very strange and application specific. It was on finance. So this one is going to be it's going to be technical, and basically what I'll be able to during the talk, I will tell you basically everything about how things like CVX and CVX pi work, how they work. They don't work the way you think they might work, or it depends. Some people don't even think about how it works, which is good. We like that. They just use it. But I'm going to tell you everything about how it works, and it's actually much simpler than you might think. So that's today's talk, and it's going to be mathematical at points. So what I'll do is I'll start with a quick overview of what is convex optimization, and then we'll get into constructive convex analysis. And it's the question of how do you know if a function is convex, okay? Then I'll talk to you about cone representation, and that's the key, that's the trick behind how things like CVX works. Then I'll actually just tell you exactly how it works. It's very simple, actually. That's canonicalization. And then we'll talk a little bit about modeling frameworks. So these will be the ideas, the mathematics, and then this will be the software implementations. Actually, it's very nice because in real languages like Python or Julia, these implementations are beautifully small. I mean, the core of these things in Julia is something like 50 lines. Right, but that's because it's in a very powerful language, but it's really cool. Okay, and then I'll wrap up with some conclusions. So let me start with convex optimization. So it's a mathematical optimization problem. You have to choose the value of this variable x here, and then in convex optimization, the equality constraints have to be linear. So you have ax equals b, and then inequality constraints. We're going to write them as less than or equal to 0. And here, these functions, fi and the objective, have to be convex. That means they satisfy this inequality. And it just means if you plot the graph, it has non-negative curvature. It curves up. It means nothing more than that. OK. And so this is what that's a convex optimization problem. And if you study it or do the mathematics of it, you would start from this. OK? Okay, so what has emerged in the last maybe 15 years, but even more so in the last 5 years, as a standard canonical form is something called cone programming or conic form. And so what that is it's a special case, and it looks like this. The objective is linear. The equality constraints, they're still there, but all nonlinearities are put into a cone constraint. And that says that this variable x lies in some cone. Now, if this cone here is the set of non-negative vectors, so vectors whose entries are non-negative, you'll recognize this as basically a linear program. So it looks like, it's the standard form for linear. And in fact, cone programming is supposed to be a generalization of linear programming. So the only thing you do is you change this cone, and you get a more general class of problems. So for example, you could change this cone. You could have x be a matrix, and the cone could be the cone of positive semi-definite matrices. And this would be a so-called semi-definite program. So this is kind of the modern canonical form. And in fact, what it has emerged as basically the standard intermediate form for convex optimization. And I mean that with reference to computer science, right? In computer science, you have a high-level language, which is a compiler will first transform to, some intermediate level thing, like some 3-byte code or whatever it is. And then, people will optimize that. That's optimization in a different sense. That's optimization in compiler sense. That intermediate form is optimized. And then from there you translate it into some code that will actually run on a specific machine. Okay, that's how basically compilers work, right? So this is essentially, this has become the standard intermediate form. Okay. Now, by the way, just like intermediate form in code, very few people really need to know this. I mean, we still teach it in classes. I mean, which is fine. But the point is, I can imagine in 10 years, we don't even teach this, right? All we need is we need a few people to understand this because we need people to write solvers, and that's about it. I mean, the same way the rest of us use compilers all the time, and we definitely need some people who know how to write compilers and know how to write the optimization and the back end and all that kind of stuff. But the rest of us do not need to know the details. So, okay. So how do you solve a convex problem? Okay, so basic broad categories would be something like this. Well, if your problem is a standard form, like it's a linear program or a quadratic program or a second order cone program, then you just use someone else's solver, right? So the first step in solving any problem is to go to Google and type in, source code and then your problem name. And if you're lucky, you'll go to a GitHub repo, and 2 minutes later you'll type make, and you'll have actually like some software someone else wrote that will solve your problem. I mean, that's the best outcome. Now, the good news about this is that if someone writes a linear programming solver, it's used across 100 different fields for 1,000 different problems. And so basically the effort, there would be no limit to the effort that people should put into making better linear programming solvers, because it's being solved everywhere in 100 different fields, in mechanical engineering, it's in signal processing, it's in statistics, it's in electrical, it's just everywhere. It's in finance, it's in planning, supply chain. So basically that justifies putting a lot of effort into it. Okay. Okay. Now at the other extreme, you can write your own solver. Okay. And if you're a big company, if you are Google or Baidu, this is what you're going to do. Of course, because you want it to be as fast as possible, has a scale and all that kind of stuff. And that's a lot of work, but of course it's worth it. If you're, okay. Now, another method, which is quite common, and this goes way back into the 40s. So even in the first book on linear programming, George Dantzig talked about, a lot of the book talks about transforming a problem to an LP. It doesn't use the same language we use now, but it's basically the same. So people understood this from the very beginnings. And the idea is you take your problem and you transform it to an equivalent problem, but now that new problem is compatible with the solver. So that's the idea. And this extends the reach of problem solvable by standard. And this whole talk is about a method to do this automatically, right? So it used to be if you took a course in, operations research, or even my course at Stanford, a lot of it we teach people how to do these transformations, and a lot of the transformations, people would expect to do by hand. That's a pain. So these domain-specific languages completely automate that. That's what they do. So that's what the talk is about. Okay, so now we get into, well, there's going to be some math now. So, okay, but I warned you. So, all right. So what you have to be able to do, of course, to say if your problem is convex, you put it in this form, like this, and there are these functions here, and you have to know, are they convex? Suppose that's a circuit design problem, and this is the total power dissipated. And you have to know, is that a convex function of the device widths, for example, right? Or this is the side lobe level in antenna array beam forming. And then you'd like to know, is the side lobe level a convex function of the weights, right? So what you have to do, essentially, is know if some given function in an application is convex or not. So you have to determine that. Okay, so, and this is what a lot of the class, if you take a class on this, a lot of would focus on this idea. Okay, so you could use the basic definition. So you could go back and do this. You could go back and see if you could show that this is true. Right. Well, honestly, unless f is very simple, that's kind of a pain in the ass. Okay. I mean, for some things it actually works, but very few. Okay. The other option is you could do things like this. You could say if the function is twice differentiable, convexity means that the Hessian, the second derivative, is non-negative as a matrix. That means it's positive semi-definite, right? I mean, that makes perfect sense, right? Because, in fact, convexity is essentially a sign condition on the second derivative. That's what it is. The same way monotone increasing or monotonicity is a sign condition on the first derivative, right? So that's going to be a theme. It's going to come up, right? So, okay. Okay, so you could try to work out the Hessian. Now, one of the problems is most of the interesting functions that people use in applications, they're not differentiable. And so this Hessian doesn't even exist. Okay, not only that, even when it does exist, you do not want to calculate it, right? So basically, you want to throw away all of your calculus training, your pencil and paper training, and you want to use a more modern method. And the method you want to use is essentially a calculus. And so what you want to do is construct a function using a library of basic functions. So you're going to, and it's a small library. Once you learn 10 or 15 of these, you're set. You can solve many, many problems. And then you learn calculus rules or transformations that preserve convexity. So this is the approach, right? And weirdly, I call it a calculus because it is actually a calculus. It goes back to might as well be 1780 or something, because basically if you think about calculus, what it is it's a bunch of rules. It says, oh, you want to integrate or you want to differentiate something. Here's some basic things like the integral of exp or log or sine or cosine. And then you learn some rules like integration by parts or derivative of a, these are rules. And so this is the same spirit, a little bit more complicated. Actually, they're not more complicated. They're actually simpler. But okay, so here it is. So that's the program. Okay, so let's start with some basic ones. And again, you're not going to get all of this yet, but it's going to get it's not hard. I'm covering about 10 weeks of a class where students work very hard in about 2 minutes. So I hope you can't expect to get everything. So okay, here it is. So here are some basic convex functions. A power. Let's say the square of a function, okay? Or 1 over x, because that's fine. And for all of those, you just visualize it. So 1 over x goes down like this. It's got positive curvature, done, okay? Here, minus the square root, okay? The square root is actually concave. That's a negative of a convex function. And you take the minus, and it goes down like this. It's convex. Here's some, exp, negative log. That's negative entropy. So x log x, goes down, then it goes up again. It's convex, right? By the way, these are simple enough that you could take the second derivative and verify it's non-negative, okay? An affine function, so linear plus a constant, that's convex. In fact, it has 0 curvature, and 0 counts as non-negative, so it's fine, okay? In fact, you would even say this is an affine function is on the boundary of convexity. Convexity means you have non-negative curvature. If you have 0 curvature, you're on the boundary. Okay. Here's one, a quadratic form with p positive semi-definite. So if you have a quadratic form, then actually the Hessian is like 2p. So that's simple. Any norm. So any norm at all is going to be convex. The max of a bunch of numbers. It's a piecewise linear function, and it's convex. I mean, it's not immediate, but it's not hard to show. Okay, so these are basic ones. Here's some not so basic ones. The sum of squares of a vector divided by another one, and as long as the scaling factor is positive, that's jointly convex in x and y. Here's a matrix analog of it. Okay, so these things come up in statistics, lots of other areas like right away. Here's one, log sum exp. It's a function. It comes up in lots of fields. For example, I guess some people call it a soft max because it's a soft version of the max. If one of these x's is much bigger than the others, then e to the x is like way, way bigger. And then the log of it is about equal to the max, right? This is also, everyone in EE knows this because it's the decibel combining formula. So if I tell you that I said if you have some interference and it's, minus whatever it is, if it's, minus 13 dBm and then minus 25 and then another one coming in at minus 7, anybody in EE will know exactly what that is because you calculate the log sum x. Right, the x converts decibels to powers, you add the powers, and the log converts back to decibels. So, Okay, sorry, that was a dialect if you're not in electrical engineering, right? So, okay. Here, the negative log of the CDF of a Gaussian. That's a convex function, okay? Here's one that's not obvious. This has been known since 1910, okay? The log of the determinant of the inverse of a positive definite matrix, okay? So, I mean, and by the way, a lot of these things, if you're in any field like statistics, a part of your brain should be lighting up, right? This is the entropy. I mean, with some constants missing, it's the entropy of a Gaussian random variable, right? So these are all important things. Here's one, the maximum eigenvalue of a symmetric matrix. That's convex, okay? That's not obvious at all. It's not differentiable, for one thing. It's not differentiable. It's quite complicated, right? There's no analytical formula for this if X is bigger than 5 by 5 matrix, right, by Galois. There's no formula for it, right? Okay. Here's one, the sum of the k largest entries of a vector. Okay, it's a bizarre function. By the way, it comes up in lots of applications, by the way. Not lots, some. Okay, and this is convex. It's bizarre, but it is. And by the way, this even works when k is a fraction. So, yeah, you can have the sum of the 3.5 largest entries of a vector. It's the first three, the sum of the first three plus 1/2 the next one. Okay, and so that's a convex function of a vector. It's bizarre, but it is. Okay, so these are, by the way, these are not obvious at all, I don't think. This you have to take the class for. Okay, now I'm going to tell you the calculus rules. And these are the calculus rules we teach to human beings. In a minute, I'm going to show you they actually reduce to just one, which is even cooler. But for now, this is how you teach it to human beings. You say, well, look, non-negative scaling, right? If I have a function and it curves up, and I double it, of course it still curves up. So fine, that's obvious, right? If I have two functions that both have non-negative curvature and I add them up, of course the sum does, okay? And these are easy to show. If I precompose with an affine function. Here's one. If I have a bunch of convex functions and I take the max, the pointwise max, so that's something that goes like this and then something goes like that. The pointwise max looks like that and it's convex. It also curves up. Oh, this one generically introduces non-differentiability. Even if the functions f were smooth, the pointwise max is probably not because you get a point, right? So, and I should probably say that. In convex optimization, differentiability is completely irrelevant. Totally irrelevant. It has nothing to do with anything. In fact, the most interesting applications use functions that are non-differentiable. That means that your classical course on optimization, which goes like this, ready? Like, here's the gradient method, okay? Here's the conjugate gradient method. Here's the Newton method. Here's quasi-Newton method, blah, blah, blah. It goes on for a while, right? Okay, that course is essentially useless for convex optimization because these things are not differentiable, right? So, okay, so, all right. Composition, or partial minimization is one. Composition, this says that if you have an increasing convex function of a convex function, it's convex. Okay, so these are the rules you teach a person. Okay, now it turns out actually that all of these are there's actually only one rule, only one. So, I mean, mathematically it's absolutely beautiful. There's only one, and it's one, this is the only rule you need to know, and here it is. If you have a composition of a function with k arguments, and the arguments are themselves functions of a variable, then that's convex when the calling function, the outer function is convex, and for each argument, either h is affine, the function itself is affine, in which case it doesn't matter, or these could have a curvature like positive or negative, but then you have to know the second derivative, the first derivative, the monotonicity of h with respect to that argument. Okay? So that was, I went too fast. That's fine, but that's it. So the main interesting point to take away is that there's all these rules that you learn, and you should think of them that way. The sum of convex functions convex, the pointwise maximum. But the truth is, they're all one. So here, I'll show you here's a very complicated way to show that the sum of two convex functions is convex. Ready? So in that case, I take h to be the sum function. It's a dumb function. It's convex, by the way, so it's fine. So it just adds its arguments up. Okay, it's actually monotone increasing in each argument. So therefore, these things, if I have f1 and f2, they can be convex. So it just matches. Okay. So it turns out, now there's some other fancy rules that, I mean, I can't tell you all of them, but this one rule here will get you basically 95% of everything you want to do. It's a strange thing, but okay. Okay, so this thing, the way this is written is, if you're familiar with like object-oriented programming, this is essentially code. I mean, this is kind of begging to be implemented in an object-oriented system, right? Because it basically says, if you have an expression, you should look at that expression. You should ask, are you convex? And it should look and ask, is it convex itself? Then it should ask, it should get the pattern of whether it's known to be increasing or decreasing in each of its arguments, and it should call the same thing on all of its children, right? So if you know about this basic stuff, then this all makes sense. So this is almost the code. In fact, the code is actually even shorter than this when you write it in a modern language, okay? And so here's the way it's going to work. We're going to do constructive convexity verification. You're going to start with a function, but a function is not just given as a function that you can evaluate, right? It's actually given, I mean, you actually write code for it, an expression. You write an expression tree for the function. And it'll be an expression, and we'll parse it. And then at the leaves of that expression, we will have either variables or constants. Okay? Then at every node, there'll be one of our functions that will combine the children, right? And that's the idea. And then as long as these things follow the general rule, then what will happen is you can walk up the tree, or you could start from the top, it wouldn't matter, but you could walk up the tree and flag every expression as either constant, affine. By the way, affine is convex and concave, right? Because it means its curvature is both non-negative and it's non-positive. So affine means both, convex or concave, right? Or unknown. That's the other thing, right? Okay, so you tag them, and then you can use the you can actually, if you figure out the signs, you can use this for monotonicity. And for example, the square function is increasing if its argument's non-negative, right? And this gives you, by the way, you can write this in a modern language in about 6 lines of code. And it will take an expression, and it will just analyze it, right? And actually, it's even simpler. All it's doing is it's annotating the sign of the 0th derivative, the first, that's monotonicity, and the second. I mean, these things are not differentiable, but if they were differentiable, you'd be annotating the sign. And this gives it to you. So it's very, very straightforward to do this with kind of undergrad computer science. So, okay. So let's look at an example. Here's a crazy function. I have no idea, where this comes up. Let's say it comes, who knows? But it comes up in some application. That's a function, and you'd like to minimize it or something subject to a bunch of constraints, and you want to know, is this function convex? Well, by the way, because of the max, it's not differentiable. So you can take a Hessian if you like, but just don't, right? It's not a good idea. I mean, actually, this one you probably could. It wouldn't be that bad, but why? So here's the correct way to do it. This has a parse tree, right? So at the top, it calls the function square over another thing, right? We call it quad over lin, quadratic over linear. Then the quad function, the quad thing is x minus y. So we'll walk up from the bottom. So the leaves are x, y, and 1. 1 is a constant, x and y are variables. And then you form max xy at the lowest level, and you form x minus y. Max xy is the max of 2 affine things. Affine promote to convex, that's convex. That's this thing. 1 minus max is concave, because minus converts a convex to a concave. That's just, by the way, that's a special rule that follows from our general rule, right, with monotonicity. It's all instances of the same rule. Then this is concave, and this is affine. So now we're going to call the u squared over v function with u as x minus y, and v is 1 minus max xy. And now we look at this and we say, well, this thing, u is affine, so we don't have to say anything more. This thing, v, is concave, and that's fine because this is convex and it's decreasing in v. Yeah. By the way, if you're not following all this, that's completely normal and that's fine. The point is, I'm making very elementary arguments about the signs of things, monotonicity, and convexity. That's it. So notice no differentiating. I haven't said even derivative. Okay. So okay. So this is the idea. And there's a student who was actually like a second-year undergrad who actually put together a lot of stuff. His name's going to come up again later. But he put together, I mean, you can actually just go to this DCP. This is Discipline Convex Programming. And And actually, what you can do is you can type in an expression like this, and it'll show you that here's the full parse tree. And it'll show you everything here. Like constant, it doesn't show. If it's an affine thing, it's got a line. If it's convex, it's got a curve that goes up. If it's concave, it looks like that. And then you can actually see things like, oh, this will tell you the sign of it on the right, right? So x, you have no, x, y, you have no idea what it is. So it's plus minus 1. 1, that's for sure positive, okay? Let's see, let's find the square somewhere. This thing is positive because it's a square over a positive thing, right? So this is the idea. By the way, if you're a student and you just want to have fun and get into a weird mood, this actually has a quiz mode where it generates random expressions that we generated. And then you have to say, is it affine, is it convex, concave, or neither? I recommend starting at level 1. But if you can do that, then you're good. Then you get all this, right? So do you use that in your class? No. You should. You should. Come on. Yeah, it's good. Okay. All right. So disciplined convex programming is this. It's a framework for describing convex optimization problems. So it just implements what I just said, right? Now it's sufficient but not necessary for convexity, right? So you can have a function that's convex, but this thing, I mean, this doesn't show it. I mean, here's a really good example. Ready? X squared minus 1/2 x squared. Well, that's 1/2 x squared, and it's convex, okay? But you cannot show it with the rules, because when you look at x squared minus 1/2 x squared, it looks at x squared, it says convex, half x squared is convex, and then it doesn't have a rule for the difference of two convex functions, because in general that's not convex, okay? So, all right, okay. So this is the idea. All right, so now I'll tell you what it is, and what I'm going to say it mathematically, but if you know about languages, I'm actually describing essentially the Backus-Naur form of a language. In the formal computer science sense, I'm describing a language. Okay? So here it is. A DCP consists of 0 or 1 objective. If it has 0, it's a feasibility problem. And each objective has the one objective has to have the form either minimize a convex thing or maximize a concave thing. Each constraint looks like this. It has expression, rel-op, relative operator, expression, and these can be convex less than or equal to concave, or concave bigger than or equal to convex, or affine equals affine. That's it. Okay? Now, I already showed you how to, the DCP will tell you whether an expression will tag it as either affine, convex, or concave, and basically now you understand the entire language, right? So expressions are formed from variables, constants of parameters, and functions from a library, right? The library is short. I'm going to show you a part of, it's like 20 different things. I mean, and most of them are kind of obvious, right? So we'll show you that. And the idea is the library functions have known convexity, monotonicity, and sign properties, right? So for example, that's the signature of that function. So for example, the square function, we would annotate. Everything's open source. You can look into all these things. It's very simple. And it would say that square dot sign is positive. Well, yeah, because square is non-negative or whatever it is, right? It would be square dot curvature is convex. That's true, okay? Then it would say monotonicity. And it would actually say if the argument is positive, then the square is increasing. If the argument is negative, the square is decreasing, okay? So that's the idea. And then basically all the sub-expressions have to match the general rule, right? So that's why a parser that verifies DCP is about 20 lines of code in a modern language, okay? Which is pretty impressive, actually, because when people look at things and they use CVX and they go, how does this work? And they say, oh, you're calculating the gradients. Like, nope, nope, much simpler, way simpler. So it's that. Also, by the way, when something comes down to one rule, it means when the core of something is 40 lines of code, not only is that mathematically beautiful, because it means it's extremely compact, but it has an exceedingly high likelihood of being correct, right? If someone writes code that's this huge spaghetti thing that goes like, oh, if you see a max, you should do this. If you see log sum x, oh, you could do this. That code is never going to work, ever. I mean, it might eventually, but there's going to be a lot of pain and stuff along the way, right? So it's actually, for me, it's absolutely beautiful because it both matches the mathematics flawlessly and it has an unbelievably high practical benefit, which is called correctness, right, with high probability, right? Actually, with probability 1, but that's okay because it's correct. Okay, so yeah, yeah, just correctness. Okay, so a disciplined convex program, these are convex by construction. Now, by the way, this is not the way you might think of doing this originally, and it's not the way we thought of it. So I should explain this about optimization. So there's one, the classic idea of optimization is the client-server model. That works like this, okay? I have a problem. I'm in a practical field, okay? I do, who knows, wavelength division multiplexing, and I have to assign, I don't know, I have some practical problem, okay? And then it's a practical problem. I want to like assign wavelengths or set powers or I don't know what I want to do. And then so I go to you and you do optimization. And I say, here's my problem, and I give it to you. I say, these are the variables, please optimize them. These are the constraints, and this is the objective, okay? And then, so I'm the client, and you're the server. And you do not have the right to say, I don't like your problem. Yeah, your job is to take my problem and just fix it, right? So if you believe in that model, and that's the classic model of optimization, how it's used, right? I mean, what happens is, in that model, you would do something like this. Since you don't have the authority or right to question my problem, because I'm the expert, right? What will happen is you would take that problem and hope that it's convex, right? And so I would go away, and then you would come back the next day and say, I've got really good news, or I've got bad news, or something like that, right? So it turns out, actually, if you just take a general problem written any way you like and check if it's convex, of course, most of the time it's not, right? So it turns out this client-server model is wrong. The correct way to do it is you take the people who do the applications and you teach them this, and then they can build stuff themselves that actually is going to be convex and work. So, and it turns out that's actually the better way to do it. It's not obvious at first, right? So, okay. Now I'll tell you a little bit about cone representation. So cone representation, this goes back to Nesterov and Nemirovsky. So that works like this. You have a function f, and so actually the real question is in these things, how do you represent a function, right? For example, here's a bizarre thing. You'd have something like CVX, which is one of these systems for solving convex programs, and then you could do things like this. You might say, you might just use it for a while, and after a while you might get curious and say, how does it work? And you go, I know, somewhere there should be like a gradient in there, right? I mean, come on, it's optimization, there should be a gradient, right? So you can actually like search for the key term gradient or grad through all the lines of code, and it won't be there. So there's no gradient, not one. There's no derivative, there's no calculus. Nothing is there, right? So now I'm going to explain how that works, okay? It's very strange, right? Because if you think about optimization, I mean, you go back to the classical thing, it's like, gradients, or, who knows, second derivatives, or I don't know, whatever, this kind of thing, right? There's none, absolutely none in these systems, okay? There's not a concept, okay? So it works like this. You represent each function as the optimal value of a little cone program like this. Here, y is an auxiliary variable, and this is a little baby cone program that if you solved it would actually give you the value of that function. So that's a cone representation. It's a really very cool idea. And then you have to work these out, and these are not obvious at all. But the good news is exactly like the JVM. Only a few weird people have to know about these things, and then the rest of us can use them. Okay? So here's an example. This is the geometric mean. It's concave. So this is a convex function, negative geometric mean. Okay? How do you represent that as a cone program? Well, it turns out, by the way, this is all due to the Nesterov and Nemirovsky. So these Russians. This is all from Moscow in the 80s, something like 70s. Okay? So you write it this way. If you minimize the variable, the objective minus t, subject to this is a matrix inequality. It says that thing's positive semi-definite. You will actually get the negative of the geometric mean. Okay? This is not obvious. It's not hard, though. I mean, that's got to be positive, and the determinant has to be positive. The determinant is xy minus t squared, and you're almost there at that point. Okay, here's a bizarre one. Remember this function, the sum of the largest 3.5 entries of a vector? It's convex. But here's what's not obvious. it is the optimal value of this linear program. It says minimize the sum of these lambdas minus k times nu, subject to this equality constraint and these inequalities. I mean, who knew that, right? I mean, actually, you can know that, but it's, it's complicated, okay? But the good news is this. For library elements like sum largest, somebody does this once, and everyone else will use it, okay, without knowing what it is. Okay, so even I've forgotten some of these, even though, and we just get them from, we either figure them out ourselves. If it's very hard, we send email to Yuri Nesterov. And if he can't figure out a cone representation, then we declare it for practical purposes to be not representable. So that's what we do, yeah. So there's very few of those functions, but there's a few of them, and I've even forgotten what they are. But okay, so, all right. So there's SDP representations of crazy things, right? Not just the sum of the 3.5 largest entries, but things like this. The sum of the k largest eigenvalues. The dual norm, that's the sum of the dual of the spectral norm of a matrix. That's the sum of the singular values, okay? I guess it's called the trace norm and things like that. So these things are just, they're not obvious. And here's the cool part. You do this once, it's mathematically correct, and then everyone can use them, including us, and we've totally forgotten the representations. I don't even remember what they are most of the time. I mean, I could probably reproduce most of them, but it would take me a while. And the good news, you don't have to, right? So that's it. Okay, so now I'll tell you about canonicalization. You start with a problem in DCP form with cone representable library, and then you automatically transform to an equivalent problem. So this works like this. It is so dumb, it's unbelievable. It goes like this. Remember, we're up to about 40 lines of code in a real language. 40 lines can analyze your problem, tell you if it's convex or concave. That's all. Beautiful short code, and it will be absolutely correct because it's so short. Okay? So the way it works is this: is you walk through your library, and whenever you find a non-affine function, you simply substitute its cone representation. That's what you do. It's that dumb. Then you get a new problem, and the new problem, you transform it to a new problem that has nothing but linear equality constraints, and has linear equality constraints and has cone constraints, and that's it. Now it's in the form for a cone solver. You throw it to a cone solver, and it solves it. Okay, so that's the idea. And by the way, it's the DCP property that tells you that actually the new problem is equivalent to the original one, right? So that's how that works. I mean, it's quite interesting, right? How this works. So basically, what it says is you could build a working prototype, of something like CVX or CVX pi, and it would be about 50 lines total in a modern language. Okay? So I mean, in a fake language, in something like MATLAB, it would not even work. I mean, because they have an object model, but it's not right and all that kind of stuff. But in a modern language like Julia, Python, it's nothing. Right? It's really short. It goes straight to the mathematics, and therefore it's correct. Okay. So this is the idea. By the way, it's a completely hilarious thing to do is imagine what happens when you solve a least squares problem with CVX. Least squares problem is the oldest convex problem there is. It's from 1805 or whatever. It's either from Legendre or Gauss, depending on how you feel about the history of it. But the point is, it's 200 and something years old. 300. Did I get that right? 1900. Yeah. Okay. 3. Okay. Fine. Okay. So it's hundreds of years old. That's a true statement. Yeah. So okay. So it's the oldest one. How do you solve least squares? Well, you set up the normal equations. It's a set of linear equations, right? So everyone here knows how to solve least squares, right? It's pretty straightforward, and you can solve it exactly because you just form a set of linear equations, use Gaussian elimination, you solve it. Do you know what we do? This is hilarious. So CVX will take a least squares problem, the simplest problem there could possibly be, because and here's what it does. It converts it into a second order cone program. That's a complicated, non-differentiable convex optimization problem that wasn't even known 15 years ago. Okay? Then it fires up a very sophisticated, primal dual homogeneous embedding solver, and then that goes for 22 iterations, and it computes the solution. Is everybody following me? So it's just unbelievably complicated. Oh, also I should add, the problem you're solving is way bigger than the original problem. Okay, so this doesn't sound good, right? Okay, turns out here's the weird part. That's wrong. It's fine. And the reason it's fine is because when you do the canonicalization, you might start with a problem with 20 variables and end up with one with 1,000. But the one with 1,000 is super duper sparse. And modern solvers will exploit the sparsity, and it turns out there usually isn't really an overhead. I mean, it's like 2x or 5x or something. I mean, we'd shoot for being 10x slower than a custom implementation. So actually, I once went to a conference and explained what we were doing. We said our goal is to be 10 times slower than the state of the art. And then someone raised their hand and said, maybe you have jet lag, but don't you mean to say your goal is to be 10 times faster? And I'd say, oh, no, our goal is to be 10 times slower. And they thought I was bizarre. And finally I explained, oh yeah, no, we want to be 10 times slower when it runs than state of the art, but we want to be 10 to the 6 times faster in coding, right? So instead of having 3 person years of writing C++ and tuning it, I want something that even a professor, I was going to say a grad student, but even a professor could type in a script and everything. Actually, I pointed that out. It's changed a lot of things, right? Because we used to, right? I mean, we're not going to be writing C++, right? I mean, right? So, but these things are so short and so simple that, in principle, by the way, if you're a grad student, you should be nervous, because this is like, if the professors don't need you anymore. So I'm just saying you should be a little nervous about this, just a little bit, right? So, okay. Okay, so now I'll tell you about modeling frameworks. So we'll look at a problem, and I'll explain. So I just told you all the theory of how these things work. Now you know everything. Okay, there's nothing else. So we'll go through and I'll tell you about some of the, I'll show you the actual software implementations that do this. So here we're going to look at this problem. I mean, who the hell, I don't know what it is. Look, this is a least squares problem plus an L1 norm. So that's like a lasso, problem. Except I'm going to bound all the coefficients between plus and minus 1. I don't know why, right? But it's just an example of a problem, okay? It's convex. And I have some parameters like A, B, and gamma. Gamma, by the way, has to be positive, right? Otherwise, if gamma is negative, this is not convex, right? Okay, so that's our problem. And, and this problem, if I went to Google and I typed in, lasso with, whatever, parameter bounds, okay? I'm not going to find anything, okay? If I want lasso, I'm going to get outstanding solvers, right? And they're going to be custom made for that problem. They're going to be super fast, and, they're going to run on a GPU or whatever. It's going to be really good. But not this one. So that's why we picked this, right? So, okay. All right. So in CVX, which probably a bunch of you have used or seen, is MATLAB. And it's an embedded DSL. It's an embedded domain-specific language. It's in MATLAB. So it's just part of MATLAB. And it works like this. If you want to specify that problem, you say CVX begin. Then this declares x to be an object. It's a variable of size n. This has no value, has no numeric value, right? If I type x at this point interactively, it'll say it's an optimization variable. It does not have a numeric value. Then I form this. It says minimize the sum of the square of this thing. And this thing would be CVX. When you hit CVX end, it will parse all of this, make the parse tree. It'll convert it to a cone program. Again, you don't need to know that any more than you need to do. You don't need to know what happens when you type make or whatever, when GCC runs, or the JVM runs your byte compiled code. I don't even know. I don't know what happens, right? I don't know how LLVM runs these. I don't know how this works. I know my very sophisticated colleagues in computer science do know, and I also know that their implementation is with exceedingly high probability correct. That's the critical part, right? So same thing here. Most people, you don't have to even know cone program. In fact, I like the idea. I don't know what the number is, but probably 95% of people who use these things don't know. If you said, what's a cone program? They'd say, I've never heard of it. For me, that's great. I love the idea because it means it's gone down in importance, and it's just an intermediate form. It would be like someone using, I don't know, just in their first class and asking, how does JVM work? And the answer is, I actually don't know. I don't know, but I know it's a thing. There's a well-defined semantics, and there's perfect implementations, and so on. Okay, fine. So this is CVX. Oh, a side effect of this is it'll solve it, and then it will overwrite the object x with a vector of doubles, which are the optimal values. Okay, so that's what happens. Okay, here are some library functions. They're kind of obvious: pnorm, square, square pos, the positive part, the sum. There you go. There's sum largest, right? And so you could just freely use this and have absolutely no idea how problems involving it are solved. It's very cool, actually, if you think about it, right? Let's see. Square root is there. Inverse pos max. Quad over ln is our famous function x squared over y. Lambda max. Huber is a function that is it's quadratic, and then it is extended linearly, and it's used for robust estimation and statistics. Okay, so these are some. I mean, there's not that many more to tell you the truth. The total library is probably 50 things, and at least 5 of those are there just for us to show off, right? Because some of them are weird things like the sum of the 4.8 largest singular values of a matrix. Now that is never going to have a legitimate use, I think, but it's just there because we know the cone representation, which is to say we got it from Nesterov, and so we typed it in, and it's just to be weird. Okay, so okay. Now CVX Pi, this is much newer, and actually, if you're a student, number one, you should be using Python. You can use MATLAB, but please switch as soon as you can. You can keep doing. You can keep using MATLAB. That's fine. No, keep using but please spend an hour a day of quality time learning Python. Please, because you won't be taken seriously if you continue that way. So, okay. And I know I'm from a field where, originally from a field where people use MATLAB and don't know that they should be embarrassed. Okay? So, but please start learning a real language. Oh, the other option would be Julia. Right? Yeah, that's fine. That's in fact, that's even cooler. If you learn a little bit of Julia and you mention that in the right circles, your status will go way up. So, yeah, and that amount you could learn in just 1 week, 1 hour a day. You write a little bit, write a couple programs so you can pretend, and then you hang out with the right people in the right crowds. You don't say this in the wrong crowd, but in the right crowd, they'd say, "What do you program?" You go, "Well, I've been doing a lot of stuff in Julia lately," and then everyone will go like, "Whoa, wow!" And then you say, it's really convenient because you can grab the entire abstract, syntax tree from any expression. Yeah, you just learn a couple of those things to say, which you get on like Stack Overflow or something. You drop those, and your status will go way up. Trust me. Okay. Yeah.
Steve, maybe you can also mention that we should stop using R.
No, actually, so R is weird. That's true. It's a weird situation. It's a weird okay, so I have a lot of friends in statistics. I know. And so R is morally good because it's open source. But my computer science, so that's good. My computer science friends, though, were not super duper impressed by R. So I actually once had a student, I said, well, it's not going to kill you to do R. And then actually he didn't talk to me for like 2 weeks after that. He was so angry. I mean, he was in computer science. And he was like, I'm like, what? I said, what? It can't be that bad. It doesn't look that bad to me. And he was like, you don't know anything. And I was like, okay, fine. So apparently, yeah. So, but it's.
I agree with you. All the Python and the Julia,
Yeah.
is brilliant.
Yeah, yeah. But by the way, there's a CVX-R that's coming online right now.
Okay.
So right now, yeah. It's okay, fine. Okay, so Python. First of all, start learning it if you're not already doing this, right? Okay, but then, the idea is this is embedded in Python. And actually, it's a different structure, and it's actually much closer to what I believe is the mathematically correct formulation of these problems. So unlike CVX, I mean, CVX is fine. It's like the Excel for convex optimization, right? You want to just type some quick things in and make a calculation. You use CVX, right? I mean, that's fine, right? So this is the real thing. And the way it works is actually really cool. So variables are objects that live outside of problems, which is very cool, right? Then you can form expressions, and they have they're not tied to any problem. And then the way I actually think of it is this. I mean, I actually think of the mathematics in an object-oriented way, because that's actually correct. And the way it works is this. That's an expression. This minimize is a constructor for an objective. Okay, I'm going to go into dialect if you don't mind. It's a constructor for an objective, and it takes as argument an expression, and it returns an objective object. So, for example, objective.sense is minimize. It could have been maximize, right? And then it's got its object. Then you make, this is a list of constraints. Now the list only has one constraint. So we overload less than or equal to so that expression relop expression returns an object of type constraint. And that is mathematically absolutely correct. That is exactly the right way to think of it. So, and I like the idea that the math and the computer science actually have utterly converged. They've completely and beautifully converged. So that is a list of constraints. It's only got one, and if I wanted another, so I just put a comma and I put another constraint. For example, I could have comma this, and I could write sum of x equals 1. And that would be perfect. It would work perfectly. Okay? Then I construct, that's a constructor for a problem object. That's a problem object which has an objective and a list of constraints. It is not solved. That's simply a problem object just sitting there by itself. And then you call the solve method on it, and that causes it to be solved. And as a side effect, it causes the variable x, which is an object, to have its field x dot value overwritten with doubles or whatever it is. Whatever it's a bunch of doubles. So if that made sense to you, good. If it didn't, then you need to start learning some real languages. Okay. Yeah. Okay. So this is the idea. This is relatively new. And you get all sorts of very cool things. So this supports parameters. Now, often in a convex optimization problem, you have parameters, and you want to solve many instances of the same problem with different parameters. So for example, in statistics or machine learning, you'd have a loss and a regularizer, and you'd scale the regularizer, and you'd solve many versions of the problem with different regularizers, and then you'd do cross-validation to see which one you like. If you're doing control, you'd have if you're doing finance, you'd have hyperparameters, and you would solve many, many problems, and you'd vary the parameters until you like what you get. Okay, this is extremely common, right? So in CVX, you have to reparse everything. In CVX-Pi, you don't. So the way you would do that is, for example, this would actually just solve the entire problem, right? So what you'd do is you assign, you'd simply have a loop, and you would assign a value to this is a parameter. Then you call the solve method, which will use the current version of the parameter value, and then you get, and this, when you execute this, it'll actually just calculate the entire trade-off curve, right? Oh, by the way, because it's a real language, you could do the following. With one more line, I could do this in parallel using like multiprocessing, right? So this is the real advantage, is that I can go from this to, I can do the same thing in MATLAB. It's kind of stupid. Reparse it each time, but so what? Parsing is fast, right? So, but I could actually do this thing now in parallel, and I could do it on, I could do a trade-off curve, and I could do a hyperparameter search, and I can run it on whatever 64 threads, and it's 3 lines. And so it's real. So that's the, okay. All right. So in CVX-Pi, there's signed DCP. So Square knows that if its argument is positive, it can consider, if it knows the argument is positive, it knows that Square is increasing. Okay? And that means it's going to match more DCP rules. Okay. So I'll finish up. So, okay, well, let me just finish up. So disciplined convex programming, it's a formulation of constructive convex analysis. That's the mathematical, that's how you describe the mathematics of it, right? And it's really simple at its heart. It is really simple. You have a handful, you have a library of functions, max, min, sum, I don't know, norm, maximum eigenvalue, sum largest, square root, power. I mean, it's a short list. It's like 30, 40 things, right? Of which you'd only use 20 in most practical applications, okay? And then each of these, you have to know the convexity and the monotonicity. Now, you can assemble expressions that describe constraints or objective, but you have to follow this one rule. If you follow that one rule, then you're going to construct a problem, which is actually, it's an undergraduate exercise. It can be parsed instantly and transformed automatically to a cone program and then solved. And it all looks like magic. So now you know the secret. I mean, literally, you know everything about how these things work now. There's nothing else there. Okay, and what it does, of course, is it makes rapid prototyping easy. So this, I taught a class on convex optimization before we developed these tools and after. And it changed everything. Before, of course, we want to have numerical, practical applications. But it's a real pain in the ass. You can't ask the students to do things because they would spend a huge amount of time actually transforming manually their practical. We'd say, here, make a FIR filter design. No, fine, okay. But then all the code is long, and you're stuffing matrices in, and then you call some linear programming solver at the end. That's not teaching the right thing. So this changes everything. It's 3 lines. 4 lines, whatever it is. The plotting is more, usually, right? The plotting code is. So the point is, what it means now is in the class, it's really simple. When you take that class, by the time you get out, you cannot get out of it. It doesn't matter what department you're in, you will design a filter. You will do machine learning. You'll do statistics. You'll do vision. You'll do control. You'll do finance and all these things. And they're all 3, 4 lines, and you'll be doing very sophisticated things using this. By the way, also for research, it's unbelievable, right? Because for research, it used to go like this. In my whiteboard, I'd be there with some grad students. We'd put something up, and I'd say, oh, that's convex. And then, I would go home, and then the students would work all night to try it, right? And then I'd come in the next morning, and they'd say, oh, it didn't work. And I'd go, oh, too bad. So it's fine, right? But now, it's like 3 lines, right? So it's much faster, right? So, okay. Okay, so the references are you type anything in related to this, and Google will work just fine. So you'll find things about this. By the way, things like these things are all completely open source. There's a convex.jl, that's the Julie, and there's CVXR on its way. Yeah. Sorry, but I have all these friends who are statisticians, and I have weird mixed feelings about R. It's
root R as well.
What?
Also root R code.
Yeah, I don't understand any of it. When I look at it, I'm like, I have no idea what that is, but that's another story. But okay, all right. So I will quit here, and I would be delighted to answer any questions about this or anything related.
Thank you so much, Stephen. Wonderful talk. Any questions that any of us have for Stephen? Go ahead.
Steve, understand this talk.
Please use the mic.
Steve, understand this talk is for non-optimizers, right? It's
Yes.
good promotion for convex optimization. Here you mentioned that, okay, we can write 40 lines of codes and we probability 1 to be correct.
Yes.
But then you call something else, the algorithms.
Yes.
Maybe with probability 1, they are wrong. We have an assumption that we can solve conic programming.
Right.
But that assumption actually, is questionable.
Yes.
If dimension is high, not only 10 times slower is infinite times slower, maybe you can comment a little bit about the conic programming case. Those cases, they got excited about convex optimization.
Right.
When they run large problems,
Yep.
they have to wait millions of years.
Absolutely. Yeah.
A
So
little bit warning, right?
yeah. So
Thank you very
that's a
much.
good point. Usually, I get away with not mentioning that because no one brings it up. And people say, do cone program solvers work? And I go, yeah, which is a lie. They usually work. I mean, and they can be made very reliable for some of them, and they're running in real time in a lot of systems. So you can actually do that. But it is true that they don't always work. So it's a combination. So it is a lie for me to say they always work, although I say that. Because I don't want to worry people who want to, there's somebody here who's just in some application field, they want to use this. So you lie, and you say something a little bit better than what it is. Then I go back to my friends who work on cone solvers, and I say, look, I just told a whole bunch of people in this field over here, like in radar, that if we can actually solve these things, so you better get working on it. So it's there's some social engineering there. Yeah, and it works fine.
I'm co-optimizer.
Yeah.
Maybe it's
Just-
not
okay, yeah. So
allowed to say
no, you're absolutely right. And I should say that what we do is we usually, these things actually can usually target multiple solvers. Now, of course, they should all get the same answer. And they usually do, like more than usually, like 99.9% of the time. But every now and then they don't. And then we actually tell the students, like when that happens, they must tell no other person outside if it failed. That when they leave the class, one of the agreements they make is very simple. That when people say, does it always work, they should say, yeah, even though it's a lie. But if they meet people who work on solvers, like you, then they can speak freely about it as long as it's not in public. Yeah, so that's the idea, yeah.
Understand.
Yeah,
Thank
so,
you.
yeah. Sure.
It's a good way to do social engineering. I didn't realize that there's a social engineering.
Yeah,
Now I learn.
yeah. Oh, and for the rest of you, no, they really do always work. Yeah.
I just want to clarify two points. But one thing, when you say you do this, you don't mean they have to do this. The CVX does all that.
Yeah.
So they don't need to do that.
Yeah.
The other thing, when you talk about from what the functions that you have in CVX, it looks like you have the max, but you don't have a function when you have a sequence of convex.
Or you can
so you just use the max.
You can construct that easily with max.
Max. Yeah. You just a max of functions.
That's
right?
it. Yeah. So yeah.
So you don't have. You cannot. Say
That's right.
From here to here is that function from here.
Yes.
to there.
Yeah. Well, although it's very easy to rewrite that as max.
It's max.
Right.
That's
So
right.
so
Just
yeah.
the max of-
That's exactly right. So yeah, you have to use what this. You have to remain in this tool set, right? So yeah, yeah, that's right.
Professor Zuckerman yesterday with his students talked to Professor Boyd, and then the students and Zuckerman started to work through midnight. Already get going. Amazing. Very, very good.
Yeah.
Any other questions from students? Feel free to ask.
Yeah.
He's a very friendly professor.
Professor Boyd, I have two technical questions.
Yeah.
Okay, the first one is about how do you optimize the tree, the rooted tree? For example, if I have a linear program, well, we all know linear programs easy to solve, but what if this linear program has exponential number of constraints with respect to the variable size?
Yeah.
Then as your tree grows, it will not definitely grow towards the end. So can you sort of like truncate and still get some desired, insightful solutions by cutting the tree?
It's a good question. Let me answer, because it brought up some issues there. The first thing is people say, how does CVX or CVX pi solve these things? And the first thing that I have to say is CVX, CVX pi, convex.jl, CVXR, they don't solve anything. They have no solution code whatsoever. All they do is they take your problem, written in this very special form. Oh, and by the way, for the students, do not worry about, you do not have to know any of this. I just told you the internal details. The vast majority of people don't know. You have to know that one rule, and you have to know the library. All the other stuff in there, you don't have to know one bit of it, so don't worry about that. Okay, so back to this. There's no solution code. All they do is they transform your problem into an equivalent problem, and then we call someone else's solver. Now, okay, sometimes it's our solver because we wrote it, but you could link it to a commercial solver or to some other your favorite solver. So we don't do that. If you have something with exponential stuff like that, then yeah, we're going to just walk the tree, and it's just going to run out of memory at some point and stop. So that's what's going to happen. So it's not smart. This is not smart stuff. It's very well. I tell you another one, because it's so close to compilers, right? I sat down with my colleague in computer science who actually works on compilers. And he goes, yeah, I get it. That's cool. And by the way, it's the simplest language. In terms of language, it's extremely elementary, right? And then he said, oh, that's great. And once you get the tree, for this, I guess you do operations to optimize it, to get a more efficient LP or whatever it is, right? And I'm like, and he says, well, you do optimize it, right? Because that's the whole point of a compiler, right? Is they make intermediate form, and then they rearrange all the operations and stuff, and fill pipelines and crazy stuff. And they said, well, what optimization do you do? And Stephen Diamond and I looked at him and we were like, none. So these are very simple things. I mean, we should do it, but we don't.
Right. And the second question is also technical.
Yeah.
So Nestroy, he looked at first order optimal algorithm, first order, because I think he recognized that SDP, their bottleneck is in the inversion of the Hessian matrix.
Yeah.
So how could those developments be factored into this kind of software?
They already are.
Proper.solve.
It's already done. So one of the we made a solver called, it's called SCS, so self-scaled cone solver. And it is a first order solver that solves SDPs very slowly, but it solves them. But it's a first order solver. It's based on ADMM, and it links to this. By the way, it runs on GPUs and multi-core machines and things like that. So it'll scale to very large problems. It's first order, so it doesn't get super high accuracy, but it works. So Again, this is agnostic as to how you solve it. You could use a first order method, second, you can use simplex, interior point, we don't care. All we do is we emit a problem that's equivalent to your original problem, and it's your job to go find a solver for it. We have some, and we've written some that kind of work, mostly, right? I mean, you're supposed to say 100% of the time, but that's a lie. So you can use first order solvers, no problem.
Got it. Thank you. Yeah.
Sure.
Other questions? It must be that you explain everything so clearly, huh?
Okay, because maybe I ask another technical question, right? You mentioned that it's a very specific question. Here you do cone representation, right?
Yeah.
For example, this nuclear norm, this is K norm, K finds K norm. Once you do the cone representation, the number of constraints is huge.
Yes.
Actually, in very efficient numerical computation in the codes we want to write, you do the reverse.
Yeah, exactly.
To de-cone
Yep.
representation.
Okay, right.
Otherwise, very quickly
Sure.
you'll run out of memory.
So, I'm going to mention something, but only because you brought it up.
Because people didn't ask questions, that's ask. Otherwise, I shut up already.
No. You asked. It's a great question, and I'll explain. So in the next, we're going to be releasing CVXPy 1.0 very soon. It's already on GitHub. You could find it on the unstable branch or something. And in fact, it does not always compile to a cone program.
Okay.
So it will also compile to other canonical forms, including ones where you keep something like you keep anything that you have a proximal operator for. Excuse me, this is going to get technical. So for that you have a proximal operator, right? Or subgradient or something like that. And so for first order methods, the new version is actually going to handle that.
Yeah, that's what we are doing
Yeah.
all the time.
Yeah. So basically, but the point is, this will be a front end for what you're doing all the time.
That's right.
That's what you want.
Yes,
right?
sir.
So when you write like your proximal method, your 12 colleagues read it, right? And that's great. But this will be cool because when you write that proximal method, the new CVXPy 1.0 will be able to target your thing.
Yeah.
And instantly people from vision, radiation
Too many people
oncology,
read it, yeah.
they will be able to use your algorithm immediately. So that's
right.
kind of cool.
Yes,
Yeah. But by the way, it totally goes against the story I just told. So
Yeah,
that's why I didn't want to say it.
Thank you for your talk, Professor. I have one question concerning other aspects of the optimization problem.
Yeah.
Today you mainly talk about convex optimization, but I'm more concerned about non-convex optimization problem.
Good.
So nowadays,
Good.
People do many researches in deep learning models. So
Great.
in those
okay.
contexts, we mainly deal
Good,
with non-convex optimization problems. We need to pay a lot of efforts in tuning the parameters,
Yep.
and we finally may get some local minimum, but we don't know whether we can find
That's right.
any answer better. So do you have any idea about solving those
first of all,
problems?
thank you for bringing up this topic. This is great because it's a very important one now, right? So I'm going to take your questions and just say that there were some topics that each of which should be addressed, right? So the first one is non-convex optimization, right? It is so so this I would say this. So by the way, people are using non-convex optimization all the time right now. For example, in areas like deep learning, where, as far as I can tell, every problem is non-convex. But it's working just fine, as you may have noticed, right? So did they know they got the global minimum? They don't. I don't think they care, and they don't even care to minimize the objective. What they really want is a model that predicts well when you check it out of sample, right? So if I make something that classifies things, that takes a vision system and says that's a dog, that's a pedestrian, that's a manhole, then I don't care whether I minimized my risk plus my regularizer globally. And that's just fine, right? So that's fine. I still think, actually, that it's very good for people to learn this stuff. It looks like, this is like linear algebra. Not many problems are exactly linear algebra problems, like least squares, linear equations, eigenvalues. But, they come up, and they're very useful to know about, and you better know them. So I would consider convex optimization to be on the next level there, right, because they come up. So there are a lot of times when something is just convex, and if people don't know about it, then they go off and train some, 52-layer, CNN or something like that to do it. I don't know. I think I've seen things that are probably not the right way to do it. So anyway, so that's my take on that. I feel like people should know. People I know who know convex optimization, but are also perfectly okay with non-convex optimization when needed, like when they're running, when they're building a neural network or something like that. These people, at least in terms of street fighting, cannot be beat, right? These are they'll switch back and forth. They'll say, oh, okay, this resource allocation, that part is convex, but I'm going to use my neural net to make predictions of these things. And people who just go back and forth between those and put those together are the ones who can really get good stuff done. So anyway, okay, I don't know if that made sense. Your thing. So
we have a question in the back.
Yeah.
I have a specific question, actually. I'm a student of analog IC design.
Mm-hmm.
So I started reading the work of Maria Hershenson.
Yeah.
I was your student in 2001. So I have a question. I mean, what's the real challenge? Is it the difficulty of why the convex optimization is not popular in industry? Is it difficulty of converting the equations into polynomial form, or is it the inaccuracy of the
models?
The models, yeah.
Yeah.
So if you were to proceed, I'm really interested to work in this area. So so what do you work with? I mean, because they the analog circuit designers, they're using second order equations, or the short channel effects are now increasingly more. So I hope you.
So that's a good question, and it actually comes down to the heart of some of these things. So actually, you're talking about specifically in analog and mixed signal design. So actually, it is used. So people have full synthesis paths that use this, like full synthesis paths, right? So it actually is being used, but I'm talking about this. You can. There's an approximation of some circuit design problems that are convex when you transform the variables, and that's what he's talking about. And so that actually is used. It's not convenient to map these, but with tools like this, it's a lot more convenient, right? To do this. The second part of your question, which is actually a very good one, which is this, is that the so-called real problem is not quite convex. That's true. I mean, for example, in digital circuit design, the gate sizes are not a double. They have like 6 or 10 different gate sizes. That's it in your library, and you got to use one of them. So you have to quantize the gate sizes, right? By the way, same for analog stuff. Like you have numbers of fingers in a device, and they're integers, right? So the way people do this usually is you just start with some approximate. You ignore the fact that some things are integers. We were talking about this yesterday. And the nice part is you get something that actually really works. Then usually there's a simple heuristic that will round them and then maybe adjust a few things and stuff like that. And so people have done very well with those methods. I should also add that there are lots of cases where you have that. We just don't talk about it. So here's an example in statistics or something. Suppose I want to make a classifier problem, and I have all these transactions, and I have a vector of 100,000 features of a transaction, and some are marked fraud and some are not, right? So, and I want to make a hyperplane that separates them. And I'd like the hyperplane to separate as few things as possible. That's not a convex problem. It's just not. Okay? Maybe it's what we want to do, but we can't do that. So instead, we use something like a support vector machine, where you actually make an approximation of that, where instead of saying I'm going to charge you for misclassifying one, I'll charge you by proportional to the distance you're on the wrong side of the plane. Then you get a support vector machine, right? By the way, in practice, it then works superbly, right? So, but people don't talk about the fact that the original problem isn't convex, right? So that comes up a lot. And the only thing I'd say about that is it's kind of obvious when you make small approximations. Like if someone says, here's my fuel use map, and it tells me that if I have a jet engine and here's the thrust or the power output, here's my fuel drain rate. And it's going to be convex, but it might even have like a little weird wiggle in it at some point where it's not convex. Okay? If I make a 5% approximation and I just ignore that, of course it's going to work. We know that. That's kind of obvious. The history of these things is that huge approximations that are completely insane and don't make any sense have, where you would just say, like, seriously? You're approximating this by, that'd be like approximating the number 1 by the number 2, right? You're like, really? Those things often end up working unbelievably well. So I just mentioned that to everybody here. It's a famous thing. There's something called relaxation, very fancy method, sounding method. Here's what it is. You ignore the non-convex constraints. You just ignore them. You just ignore them. You just forget them. Ignore them. That's called relaxation. I mean, when you talk to someone in the field, they're going to make it sound really fancy and throw in semi-definite programming and make it sound really sophisticated. But that's what it is. It's as dumb as that. Okay? And these methods work in practice unbelievably well, right? Where you just, you relax it and then you round the final thing or something like that. I mean, these things work pretty well. So anyway, by the way, those are good points. The question is what happens when your problem is either not quite or even not at all convex. So
don't have the nano precision, but it works.
Yeah.
Go
yeah.
Can you let Frank ask first?
Okay. In operations research and management science, we use a lot of dynamic programming.
Mm-hmm.
Can the program? Can you solve the DP? Backward.
Yes. So that's actually a great question. It turns out one of the points on the slide was, so to do dynamic programming, you have to do two things. You have to take expectation, and you have to do partial minimization. Both of those operations preserve convexity. So convex optimization plays beautifully and nicely with dynamic programming. And you can use it to do approximate dynamic programming, which is even cooler. So the answer to that question is yes. Convex stochastic control. In fact, you can even write them, you can actually literally write them in with the Bellman formulation and stuff like that, and it'll actually just solve it. Yeah. No. Yeah.
It's actually connected to the first question I asked. So to optimize the tree in the software, can we do something like recognizing which constraint sets are redundant? They are contained in those that have already,
that's a great question.
How can software automation do that?
So you can do that. That is done. So all serious linear programming solvers, except the ones we write, which actually are widely used, but whatever, because we're lazy, they all have something called a pre-solve. And a pre-solve does this. It takes your linear program or your cone program or any kind of thing, and it searches through and it looks for stupid things. Like, here's an example, a variable that's never used. Okay? It happens all the time. Yeah. Okay, how about one? How about a constraint that's like just, that's 1 equals 1? Well, that's stupid. Of course that's true, so that's fine. Or it looks for constraints that say that a variable is equal to a value. Like x17 is equal to -2, right? So what it does, in that case, it just removes that variable and makes a note that we already know its value before we start. So those are, but one of the things that they'll do is they will remove, obviously redundant constraints in a pre-solve. Doing it more generally is probably more complicated. But so that is done in all good linear programming solvers. So that doesn't include the ones we wrote. But yeah, so that's a pre-solve. And it doesn't recognize all redundant constraints. That is itself more complicated than just solving the problem. But it recognizes the simple ones.
Well, at this point, I know that there's a lot more interesting questions that you all still have, but I do have to call a close to this lecture. And let's thank Professor Boyd again.
Thank
you so much.
Thank you. Thanks.